Okay, everybody, how's it going? We had a warmish day yesterday, right? Kind of nice, wherever you might have been. I hope you got to enjoy it. Are there any questions administratively about what's going on with the class at this point? So we have today, we're here, thank you for being here. Then we have Tuesday, we have Friday, those are classes, and then the Tuesday after that, that's the exam. So in terms of what we're responsible for material covered today and material covered on Tuesday. And then there will be nothing due, right? We have an assignment due on Tuesday, but there won't be an assignment, there'll be an assignment due on Friday as well. But the Friday stuff won't be due till afterward, okay? And Proj is working out the assignments and things for where you might sit. If there's anybody who wants to take the exam on College Ave that didn't get to do it, we have quite a bit of space. It's very roomy over there. So if you'd like to go over to College Ave, please let Proj know, and we can move you on over. We can fit like we did last time in here, if that's your preference, but if anyone has a preference to go over to College Ave, please make it known. Okay. Someone asked me a little while ago about why do we have hard exams? Why do we have difficult exams? And it's actually been a philosophical question that I've been pondering a little bit. And I'm not a great philosopher. But I thought about my own experience with exams, and forgive me for sharing this a little bit. My philosophy as an undergrad was that I could mess up one exam per class per semester and still be fine. Okay? And everyone has their differing ideas of what mess up means, right? But I was the type of person that when I got a bad mechanics exam, I took it and I pasted it to my closet. I was like, yeah, remember this, go get it, all right? So I thought about that though in the context of what is one benefit of having an exam? Like this last exam, we had someone get 21 out of 21 and a couple people get 3s out of 21, right? And there was quite the spread. And the goal is not to have, how do you say it? We don't want people to do poorly, right? And so I'm hoping that if you're struggling, you're asking questions here in class, you're asking questions in office hours, you're sending me messages. I think we could have more of that, to be honest. Okay, but the positive outlook is, if you're not very happy with how you did on an exam, because the exams are pretty difficult, you can demonstrate just how much you've learned, and it reflects in a score, right? Imagine if the average was 97%, okay? And one exam you got like an 87, right? Whatever, right? That and the standard deviation is like, 2. It's going to be very hard to, on the next exam, demonstrate that if the average is again 97%, right, to demonstrate that you've compensated for that prior exam. And so in my own experience, I think that's why I was able to kind of say, okay, I can do poorly on one exam per semester per class, because you can make it up on the other exams. Okay? So it's not a perfect system, and I'm all for trying to figure out how to make things more equitable, fair and everything. What I'm trying to put out there, though, is if you feel like you didn't demonstrate what you knew on the first exam, let's go out there, and you have plenty of room. Perhaps, of course, not everybody, right? If everyone demonstrates it, then that'd be great, right? It'd be great to have high averages on what we consider to be pretty, rigorous exams. But nonetheless, as a realist and with a high population value of 149, right, there's quite a bit of there's going to be quite a bit of variation. Okay, so that's just a thought as we prepare for the upcoming exam. Okay. I also tell you something that someone told me once. It's like you make the first exam really hard, then you make the second exam really easy, and you tell people how much better they're doing, how they've learned things. And then you make the final really hard. It's like, okay, that is not what we're going to do in this class. Okay, I think you'll find that it's pretty consistent. All right. If you have questions, though, now's the time. We've got a week. That's the other thing. You can do a lot in a week. And I understand you have other exams that you're balancing, so I'm sorry about that. I don't think there's much I can do about it, to be honest. But if you have questions, if you're looking at the videos, if you're watching the videos, or we're doing things in class, and it's like, I just don't get that step from 2 to 3. We might not have time to go through the details here in class, but ask a classmate, ask me, ask the TA. We're here. Okay. Any questions, thoughts? Okay. And I don't think this exam was not that abysmal. The first exam was not that abysmal in terms of where the average was. Okay. I mean, I don't know how many exams we've taken in engineering yet, but that was like the average was not, like I took exams where the average was like in the 30s and the 40s, right? Like that was not that exam. Maybe not 30s. Yeah, 40s. Yeah, there were some exams like that. Okay. Okay, so, and that's not really good, also, right? Because it also doesn't. If it's that low, then it doesn't really give you a chance to demonstrate that you've studied. All right. So there's a happy medium. So let's shoot for 70%. That's what the goal should be for this average. All right. So enough about that. There was a nice question asked about how can these shear stresses emerge on an element that a principle doesn't have any shear stresses on it. Okay, and maybe that's somewhat philosophical. Maybe it's not. Maybe it's just a context. Maybe a question of the context of what we're really doing here. All right. Just to point out a couple things, though. These elements are on structures. Okay? I mean, we can philosophize all we want and saying this is a material element and it only has a normal stress. That's great. In reality, in practice, somehow you had to induce that normal stress and that uniaxial loading, perhaps. Okay, so you had to have a bar or something. Okay, so these elements are on a structure, right? So if it's a cylindrical cross section or a cylindrical pressure vessel, right? And I pick a point there and I call it A, right? I have all kinds of options for how I would orient this element. I could orient it like this, right? I could orient it like this. I could orient it like through the surface if I wanted, right? As we were showing at the end of the last session and in the last homework problem, right? That if you have a tensor sigma, we can use these rotation matrices to be able to get sigma prime. And it doesn't just have to be about the axis normal to the page. Okay. We're going to spend a lot of time doing that because we're talking about in-plane stresses, and that's kind of the scope. We got enough issues to resolve in 2D, let alone trying to make it all in 3D, okay? So the first point is that these elements are on structures and they're at locations, okay? And they're on structures at a specific location. And once we've got that worked out, then it becomes kind of just math or some, visualization of what's happening. What do I mean by that? I mean, like, if I've got this element, right, and I've got my state of stress, and it's something like this, okay, then I kind of forget about the structure a little bit. Okay, now I'm just in my little material world, and then here, this would be that point A, if you will, okay. But I got to define, my axes, X and Y, and then, Z would be coming out of the board. Okay? So we're going to spend a lot of time today, Tuesday, Friday, talking about what's happening just at some location. We're going to really be removed from these structures. Okay, you're not going to see for now. Well, actually, that's not true. We'll have this class. Yeah, the homework problems, they do talk about a structure at a location. But what we're really getting at is what is happening at these material elements. Okay, and in terms of when you rotate 45 degrees. You take this element and you rotate 45 degrees. What does that really mean? Well, we had our x like this, right? And now we've got this x prime, right? And this could be the 45 degrees if we want, coming out. And we have our y prime coming out like this, okay? And yes, for this particular situation, we're going to have the buildup of shear stresses, okay? And I can say kind of casually, well, the math says that's going to be so because we do the method of slices. But another way to kind of look at this, and then you're going to still have these normal stresses too. Okay? This is because experience and the math, okay, dictate these results. But if you will, sometimes what you've got to think about is these stresses over here on the left, these stresses, the sigma, let's say x and the sigma y, they're still present. And it's kind of like these are your friends, and now you took your house that might have been right here, and you said, oh, I'm going to twist it 45 degrees. Well, this element, you could still visualize it as being under these two normal stresses. And what's going to happen to your house? Well, it's going to be elongated more in the vertical direction and elongated less in the, I didn't do that very well, but I meant to make the y's larger than the x's, okay? But it's going to be stretched more in the vertical direction than it's going to be stretched in the horizontal direction. And if you think about it, that means that this is going to have a somewhat diamond-esque shape, all right? Because I stretched a lot in this direction and I stretched a little bit this direction. Okay, and that's actually not very good at all because those side points should be symmetric. Okay, but you see that the result is a parallelogram that no longer has, oh, I can't see myself, a parallelogram that no longer has 90-degree angles, right? These have become obtuse, these have become acute. And that is a telltale sign of shear strain. And where there's shear strain, it's very likely that there's shear stress. Okay? So that, and you can see that these shear stresses, as we've drawn them, they are going to contribute to this type of elongation and distortion of the element. Okay. Any questions on this? Okay. Just taking kind of a little bit of a step view back and thinking about what we're doing. because we're going to spend a lot of time doing some of the math. Well, once again, many of these questions, you got to ask yourself, is it going up or down? Is it increasing, decreasing? Is it positive, negative? Before you even do the calculations. All right. Well, let's go. So today we're going to talk about what are called in-plane principal stresses. We're going to also talk about what are called in-plane maximum shear stresses. And then we're going to calculate these in-plane principal stresses and calculate these in-plane max shear stresses. We're actually going to calculate them in parts 1 and 2, but we're going to essentially analytically derive ways of calculating them in parts 3 and 4. And let's take a look at a review from session 17. Okay, so we've got these elements, right? And we have states of stress, and typically we're in 2D. So we have x, y, and z coming out of the board. So theta is about z. And we're typically rotating about z. Okay? So that we get, again, the sigma x prime, sigma y prime, and the tau x prime, y prime. Okay? And as we do this, right, it's probably not a bad idea to remember how the slicing relates to the angle of rotation. So for that, okay, if you have, and this is again why it's a good idea to use exaggerated small angles essentially. So if you have something like this, you're going to take a slice and you see this was a smallish angle here. And you see down there, smallish angle is there. And you see that this surface that we've created is going to be this surface of this new rotated material element. That's going to be essentially the x prime face. Okay? And so we see that's the angle theta there. And we can draw the sigma x prime coming out of the x prime face and the corresponding stresses. We know that if we want to go between the sigma x, sigma y, tau xy, and the sigma x prime, sigma y prime, tau x prime, y prime, the approach that we have taken so far is to use equilibrium and use method of slices. Okay, so we in kind of near the end of the last session, we said, well, there are some generalizable equations. You don't have to do this breakdown every single time. Method of slices, we can just write out these equations, and then we can go ahead and we can calculate what the sigma x prime, the tau x prime, y prime, and the sigma y prime might be. Okay? And when we do that, and I think, should I do it? Sure, we'll try to do it. I don't know if we'll do it successfully, but let's see here. That's really small. Okay. So if we go to the website and we scroll down over here and scroll up, so we kind of did this already, but it's not, at least in videos afterwards, it's not that tricky, okay, to go ahead and run. So that's just Control Enter, and then if we're down, I don't know, is this 17.3? Yeah, so we can go ahead and we can plug in, right, our sigma x, our sigma y, our tau xy, and plug in an angle, right, and get a response, get the new sigma x prime, sigma y prime, and tau x prime, y prime. Or what we can do is we can run through a range of angles. So if you look, okay, at, let's see here, you see, okay, do you see that we have a cosine 2 theta and a sine 2 theta? And so we're rotating, okay, the angle is changing, we're rotating, okay? In order to completely map out all possible solutions, what angles do I need to specify? Or what range of angles should I specify to map out all solutions?
0 to 180.
Yeah, 0 to 180, right? Because I've got 2 theta there, right? So 2 theta means 2 times 180 is going to be 360, and I'm just going to keep cycling around, okay? So that's, the math tells us that here, it tells us that here, and it tells us that here. And this 2 theta is going to come back in some other graphical depictions that we have the next time we meet. But the kind of the point is, when you're putting this into Python or whatever coding, or Excel, whatever you want to use, you can specify the range over which you're going to run these, and we're doing 0 to, let's see, we're doing 0 to 180. Now be careful, this is in radians. So if I want to go from 1 degree, I had to multiply by pi over 180. Okay, because that's how this is. That's how NumPy is handling these trigonometric calculations. Okay, but you can see that if you go from if we go through the range, like we see here, right? We're just going from 0 to 180. Okay, and then. Okay, we come back here. Oops, wrong direction. Okay. We begin to think about where we might be. So if we were to rotate by like negative 30 degrees, okay, so positive 30 degrees is easy, right? We'd be just right here. But if we rotate by minus 30 degrees, we actually go backward from 180, okay? And so we would kind of come out here, and we would come out there, and we would come out there, all right? And so we can write out what the new sigma x prime, new sigma y prime, and new tau x prime, y prime are, right? We're rotating, so this is, this is a, obviously this is a linear axis. This is a linear axis, okay? And what we're attempting to do is describe how the sigma x prime and how the tau x prime, y prime, and how the sigma y prime vary as a function of A. Any questions on this? Now, what do we notice here? Well, we notice that these are sinusoidal in nature, right? We have sines and cosines. And what else? We notice that there are peaks, right? So there are maximum and minimums. And they go through zeros sometimes, okay, like these shear stresses do. But the normal stresses, they don't necessarily have to go through zero, okay? They don't necessarily have to. But you notice that they get their peaks and valleys. These are trigonometric functions. Why do you think we care about these peaks and valleys? Any ideas? Why should we care? Yes, Mark?
It's the maximum and minimum of the stresses.
Yeah, these represent orientations that get us into looking at the maximum and minimum values of stresses. And why do things break? Because we exceed thresholds of stresses. Okay? And when we get into the criteria for failure, we'll establish some guidelines very carefully. But just so the basic idea, and this is something you can take with you, is don't just stick it in your good to know file, but stick it in your good to know for the exam file. Brittle materials tend to fail because of maximum normal stresses. Okay? So this probably won't be on exam 2, but it will definitely be on the final. Okay? Brittle materials fail because of maximum normal stresses. All right, so which ones are the normal stresses? Well, the sigmas are the normal stresses, right? So we're looking out for sigma x prime. We're looking out at sigma y prime. So the brittle materials, those are going to be the problems. And brittle materials often also, and you don't have to write this down, but this is for your good to know file. Brittle materials often are stronger under compression than they are tension. Okay? So if you want to break a brittle material, put in a tensile stress, some type of tensile stress, and you're probably going to have a lower stress to break it. But again, you're going to be looking at maximum normal stresses. So your perspective on the problem might be, this is the direction I'm pulling, but for whatever reason, some silly person put my measurement devices, and we'll talk about strain gauges, but my way of measuring what's happening in the material, they put them at some weird angle, okay, relative to the direction I'm pulling the bar, right? So then you do this transformation, and you're like, oh, yeah, this is the maximum normal stress because I've done the transformation, okay? You get where this is going? So the idea of using these transformations is very powerful because it helps us recognize the peaks and valleys and the stresses. Now, the other important thing to remember is that the ductile materials, okay, so not your glasses, not your ceramics, the ductile materials, and so, not cast iron even. It's not just metals are ductile and the glasses and ceramics are brittle, okay? There are degrees, but that's not a bad way. I mean, glasses and ceramics being brittle, that's a pretty good rule of thumb, all right? But the ductile materials, like some of the carbon steels, low carbon steels, the aluminums, titaniums, these different materials, and there are different alloys that have differing degrees of ductility. But these are the ones that they neck, right? When you pull them, they do the necking thing, right? And if you've been in the lab, have you been seeing the necking in the lab? Hopefully. Right, when you do the aluminum samples, okay, yeah, all right. So, and then the paper doesn't. When you pull the paper apart, that doesn't. That's more. It has more of a brittle failure. Okay, and you can see the tear-like nature, the jagged-like nature of the fracture surface. So anyway, but the paper does actually go a little bit over. It's not like, but it definitely does not do what the aluminum materials or some of these other ductile materials do. So anyway, these ductile materials, they fail because of shear stress. Okay, and there are different theories. There's one theory we'll talk about that's basically maximum shear stress theory, and there's another theory that has to do with distortion. But as you know, with distortion, right, when we talk about distortion of elements, that has to do with shear strain. Okay, and that has to do with shear stress as well. Okay, so that is why we're doing all this mess. Okay, that's why we're doing these transformations. We're interested in the peaks and valleys. We're interested in, this is the maximum normal stress. This is not a maximum normal stress. This is a maximum normal stress. Interesting, okay? This is a maximum shear stress. This is a equal and opposite maximum shear stress. Because remember, shear stress, there's not really tension. There isn't tension and compression in shear stress, right? It just flips the direction. So it's pretty symmetric. Like if I twist a rod one way and I twist it back the other way, if it's a linear isotropic homogeneous material, it's not really going to care. It's not going to say, I want to break this way instead of this way. It's just going to be a little bit of chance, a little bit of randomness, a little bit of statistics, and a lot of bit of shear stress. Okay, so the other thing you might notice here is that when the shear stress is a 0, whoop, 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 and here, guess what? That's where your maximum and minimum normal stress is. So they're kind of they are out of phase with each other. So when you're peaking in the normal stresses, you are usually minimizing. Actually, you are getting to a state of 0 shear stress. We're going to talk about that. Okay, you can. I'm getting a little ahead of myself, but you can always find a state. It's called triaxial stress. We'll talk more about this. You can always find a state where you have just principal stresses, meaning just normal stresses. This is kind of cool, right? So if you don't like shear stresses, that's the state for you, okay? And it may require rotating about multiple axes to get there, but there always exists a state of principal stresses with 0 shear stress. The corollary is not true, or the contrapositive. No, those are tautologies. So, like in logic, if you said the contrapositive, that would be true. But the analogy with shear stress is not true. You can't always. Sometimes you can get to a state of just shear stress. Okay, but in many cases, you're just minimizing the normal stresses, and you're finding the maximum shear stress. Okay, but you're not guaranteed for a material element to find 0 principal stress, 0 normal stresses, and just shear. In fact, only in pure shear is that really the case, right? So that would be like a rod that you're twisting. That's one example of pure shear. Or plates that the single shear and double shear. Okay. Any questions? Any thoughts on this? Yes.
You probably went over this by the last class, but can you quickly explain again what exactly this means if we're rotating it? Like, are we rotating the plane of what we're measuring, or what does that mean?
So if I take the classic example that good professors use that I did not, but someone left me an eraser, so maybe I will be a good professor. Okay. The classic example is they take the eraser, they draw on the eraser a square. Okay? So look, I'm doing it. Wow, I'm so good. I feel good. I didn't even plan this. Right? So there's the square. All right? That's a classic example. And then I pull here, and if I was a really good professor, I'd have a rubbery material, more rubbery, right? More stretchy, right? And you can see that it elongates this way, right? If I pull this way, and it would do that, right? Now, let's say that I have a state of stress, and it's like under tension this way and under tension this way, right? Which is cylindrical pressure vessel. The way to think of the rotation is not so much that we're rotating the state of stress, although you can kind of think of it that way. It's more that we're rotating our perspective. So I would then draw on this nice material element a box that is 45. There's no way anyone in the back of the class can see that. All right, but just trust me. There is a box that is rotated 45 degrees. Okay, and I put the same stress that I put on the original one, but now I have a rotated element, and that's the perspective I'm looking at. And that box, that rotated box, right, it has definitive normal stresses that can only come out of those faces, and has definitive shear stress that is just around those faces. Does that make sense? So it's more, these are, remember, we're dealing with tensors, and the beautiful thing about tensors, and tensors are beautiful things, is that their springs are made out of rubber, or their tails are made out of rubber. No, the thing is that it preserves this information as you rotate. So I can put any box with any orientation at or on this structure I want. And if I know the state of stress with that particular orientation, then I can figure out at any other orientation, right? The tensors preserve their information. Yes?
So let's go back to the angle of rotation. So if
Yeah.
we have a 180 degree of angle of rotation,
Yeah.
You treat it as 0 instead.
Well, oh, yeah. So if you get to 180, all right, yeah, you're right back smack where you were. And that, look at it, right? You're here, so let's say, okay, I go 180 degrees. That's 0. Okay, 0. And then I go 180 degrees. Boom. Sigma x prime is back where sigma x was originally. All right? Boom. Tau x y, or tau x prime y prime is back where it was originally. Boom. Sigma y, right? Sigma y prime is back where it was originally. Okay? So, I mean, and you can see that, right? If we look at what happens when you rotate an element 180 degrees, right? So now, we started off like this. Okay? And this was sigma x, all right? This was sigma y up here, okay? And now this sigma x, whoops, I don't have the abilities. Okay, this sigma x, right, is now all the way over here, but this was sigma x already, right? It's now on the minus x face, the original x face, but that's the same. The sigma y, oh, it's all the way down here, same. And the more controversial or the more confusing ones are, hey, what happened to tau xy, right? Well, look, they're pointing up here. And let's say this corner now goes down here, they're still pointing inside. So 180 degrees rotation, yeah, you're back where you started.
Right. I'm asking this because yesterday I was doing the homework.
Yeah.
And I plugged in 180, but it turns the part of the equation to negative and give me a wrong answer. So should we, if it's 180, should we always make it 0 so that it's positive?
No. But there was also, I actually corrected, there was an error in one of the collabs. So it depends on which one. There was one where sigma x prime and tau x prime y prime were correct, but I missed the minus signs in the sigma y prime. I corrected it this morning. So if sigma y prime was giving you the wrong answer, it's because sigma y prime was not actually calculated. No, I don't think so, but I could be wrong. Yes.
So it's strictly for convenience.
What do you mean it's strictly for convenience?
Like the propagation rate changes.
It's okay. So it's nice that it. So how do you say it? It's elegant and it's nice that it's convenient, but it's not. It's because the equilibrium, right? All we need is equilibrium. It's because the equilibrium works out to be the same, right? So it's like we can recognize the beauty of it, but it's not beautiful because we want it to be beautiful. Does that make sense? All right. I wish that would be nice if life were like that a lot of times. Hey, I just want that to work. No, it doesn't, it doesn't work that way. And in the lab, I have this philosophy that it never works the first time. And in life, sometimes I've gone through having low expectations, and then I'm pleasantly surprised when things work out. But it turns out that's a bad way to kind of approach life. All right, you want to aim high. You want to aim high. Yes.
So just to confirm, based on what we just said here, we were rotating it like from the right to the left.
Yeah.
In the question 4 of the homework, where it says like the
Yeah.
axis becomes the y-axis,
Yeah.
does that mean they were rotating the box this way?
That's right.
Okay.
That's what I was trying to show in the video. Right? I would say, look, x and x prime, they're the same. I took a 2D element and made it 3D. And then we said, look, it's flipping in this direction toward you. 90 degrees. Okay. Good. All right. So that was a long digression, but hopefully that was interesting for a few of you. All right. So in-plane principal stresses. What we're saying is that the faces of element in a specific orientation which have no shear stresses but only normal forces acting on the element. Okay, so I'm gonna. Why did I say forces? That should be stresses. I mean, yes, they are. We'll just say that this is it's really about stresses. Okay. Yes, there are. I mean, we can associate normal stresses with it, normal forces with the stresses, but we're talking about getting to a state where you have no shear stress. Okay, and this is in plane, so you can do this. This is fun. You can do this if you're given a 2D state of stress, right? So what we're saying here is that there's no tau xz, there's no tau yz, there's no sigma z, right? You have 6 options six stresses describe the state of stress, right? In 3D. In 2D, we've only got 3, right? Sigma 1, sigma 2, and tau 1, 2. Okay. So we are saying that we're going to figure out, right, we got to rotate this element by some amount, and we're going to call that theta sub p, such that we only have normal stresses. So that might have been the sigma x. There's the angle theta p, and now we have our sigma 1 and our sigma 2. Okay? And this is where maybe a little bit of convention gets confusing. Yes, we've done sigma 1, sigma 2, sigma 3, sigma 1, 2, sigma 1, 3, sigma 2, 3 for FEA. Now, sigma 1 and sigma, and even just 2 seconds ago I said sigma 1, sigma 2, tau 1, 2, right? But now, very specifically, sigma 1 and sigma 2 refer to what we call principal stresses. Okay? Principal stresses, and there's no need to describe a tau 1, 2 because tau 1, 2 here is 0. Okay, the shear stresses are 0. So you see this? We can go back to that that graph, and we already saw it. There were 2 angles of rotation where we got 0 shear stress, and we saw kind of these peaks in the normal stresses. And now we identify and we call them this, right? So there, these how do you say it? These theta p's are a little bit confusing. All right. But theta p1 is typically going to be the one that's closer to 0. So maybe it could be negative too. All right. So but it's going to be typically something less than 90 degrees. Okay. And then theta p2, okay, is going to be theta p1 plus 90 degrees. Why is that? Well, look, what happens? If I just rotate this element 90 degrees, what happens? Sigma x and sigma y flip. Now, something happens also to we're not going to talk about shear stresses there. Okay. But I can talk about them. They're going to flip sign. Okay. But But remember, there are no shear stresses here. Okay. So you can get to 2 orientations, essentially where just sigma 1 and sigma 2 would flip with each other. Okay. But when you found one, you go off 90 degrees from it. So you could go plus 90, you could go minus 90, in fact. All right. But in reality, what was I going to say? I was going to say something. Oh, that's bothering me. There was something I was going to say. It's gone. Yeah. So we have we can find these orientations that give us the principal stresses. Oh, that's what I was going to say. Typically, oops. Come on, where are you? Oh. All right, well, it just looks messy. Okay, so typically the first subscript is what we give the larger magnitude normal stress, and the second one we give the next one. And then in 3D, when we do 3D, we'll have sigma 1, sigma 2, sigma 3. And sigma 3 is even less. Typically. There are going to be times when we don't follow that convention, okay? But you're looking at when you're worried about whether a brittle material might fail, you're looking, okay, what's my sigma 1? Give me my sigma 1. And there are some other things you can do too with differences of sigmas and things, and we'll get into those criteria in a little bit. So let's go ahead and do a little example. Here we have, okay, and it's clear, right? Anytime tau xy is not 0, that is not the state of principal stresses, okay? Because tau is not 0, okay? So sigma x, and if they give you tau is equal to 0 there, then you're like, what am I doing? Probably trying to find maximum shear stresses or something else, which would be 45 degrees. But anyway, we'll talk about that later. But here we have sigma x equals 50 megapascals, sigma y is 100 megapascals, tau xy is 10 megapascals. So what are the in-plane principal stresses, and what is the associated angle of rotation? So this is in plane. So we got to rotate to get max normal stresses and 0 shear stress. So we want to do something like this. That's our goal. And we got to figure out what that theta p is to do that. All right? And the one way to do it is the trial and error method, right? Or the brute force technique. So we go into Colab, and you can do this. And I kind of, I played with Colab a little bit. We better keep going though. I better not go to Colab right now. But you're going to look at the sigma x prime, sigma y prime, and you're going to try to figure out, where does sigma x prime peak or sigma y prime peak? All right, and they're going to peak at the same spot. And that's my angle, and that's going to be my my principal stress, theta at theta p1. Okay, just like that. Yes.
Could we just do what we did in question 2 of 17, where you just find where the tau x prime y prime is equal to 0, and then you're gonna get an angle?
You can do that too. You can do that too, right? So that's another another way to look at things, right? And theta p2 will be 90 degrees out, right? And yeah, so as we're talking about here, right? We also know that that's where the shear stress is going to be 0, all right? And that's where the shear stress is going to be 0 as well, okay? So this is brute force, but it's nice because it gives us, hey, I go through this whole amount of rotation and stuff, and I can find these principal stresses. And these are not principled. They don't have principles about which they abide. Like ethics, that kind of stuff. These are principal stresses. So just in terms of the spelling, I'll probably mess it up at some point. So as we go through this, you can look at the script. What the script did is it simply says, hey, here's the array of all the possible values from, in 1 degree increments, I think I did, like from 0 to 180. And you can do whatever you like. And then it says, show me the max, show me the maximum value and tell me, what the angle is there. And that's it, okay? Brute force, not particularly elegant, but important and conceptually in terms of how you think about these problems. Okay, so the theta p is 79.1 degrees. Sigma 1 would be sigma x prime at 102 megapascals. Sigma 2 would be equal to sigma y prime at 48 megapascals. And the another angle is going to be 90 degrees out of phase with this one. And so we have these other principal stresses, which are the same as they are here. Okay, but notice that now sigma 1 is sigma y prime instead of sigma x prime, and sigma 2 is sigma x prime instead of sigma y prime. Okay, because we rotated the other direction. Or we rotated another 90 degrees. Right, you see it's 169 degrees or minus 11 degrees to get there. Great. Questions? Okay. Now, here's another one. Okay, if an element has sigma x equals 50 megapascals, sigma y equals 100 megapascals, and tau xy equals 0 megapascals, what are in-plane principal stresses and what is the associated angle of rotation? Okay, so here, all right, we already had, we have tau xy is equal to 0, okay? And so we can go 90 degrees off of where we are, okay, but we were already there, okay? So, and we can see that here. So this is at 90, this is at 0, okay? So, yeah, we can go 90 degrees, okay? But there were no shear stresses in the original, orientation. So we just get these original, like our sigma 1 is 100 megapascals, our sigma 2 is 50 megapascals, right? But then they can just flip the sigma y prime and the sigma 2 prime as we go to 90 degrees. All right, any questions on that? So these are probably the easier of the two to understand because the next ones we're going to look at are the maximum in-plane shear stresses. Okay. And there's a question. So let's talk about what the maximum in-plane shear stresses are. Well, this is rotation to create a state with maximum shear stress. And like I said a few minutes ago, the normal stresses in this rotated state do not necessarily go to 0. They could if it's pure shear, but given that most systems are not pure shear, I don't know. I guess it depends. It depends on what area you work. If you are a shaft expert, then okay, then what goes on your desk is going to have a lot of shear, pure shear. But if you're designing structures that are not just twisting, and I'm not judging one job over another, right? We need people who specialize in things and figuring out the material content, how do you machine these, how you get the surface roughnesses on shafts, all these things, how do you make sure the density is constant, how do you get rid of the eccentricities, make sure things are centered. All these things are there's a lot that you might take it for granted on a shaft. Don't shaft the shaft. All right, so here we have a state of stress. And what we're going to do is we're going to find an orientation or angle of rotation, theta s, such that we have maximum shear stress. Okay? What's cool here, right, is that we're only looking at one quantity, shear stress, right? When we have the principal stresses, you have like a sigma x prime and a sigma y prime. Right? And so you get a sigma 1 and a sigma 2. Okay? Here, we want to figure out what the maximum shear stress is. Now, often we do go about figuring out what the sigma x prime and the sigma y prime are associated with that rotation, okay, of maximum shear stress. But really, we just care about the tau. So it's a very similar diagram in that we have some theta sub s that we're going to try to get and achieve, and then we're going to have tau max, and we're going to have our sigma stresses associated with it. Okay. And then once again, it's like a broken record. The theta S2 is going to be 90 degrees out of phase with the theta S1. Because you can kind of interestingly see things. Remember how we said there were those two theta components in the stress transformation equations, and so we only had to go 0 to 180. All right. Well, this also means this like 90 degree rotation. Right? 2 times 90 is 180. Well, interesting things happen when you do just 180, right? This is sine of 0 and sine of 180, or cosine of 90 and cosine of 270, right? Well, maybe not that interesting, right? But 90 degrees of a material element rotation, in the math, it corresponds to 180 degrees. Okay? So here, if we have an element, and so we're essentially just repeating the same thing. We're doing brute force again, okay? We're just saying, look, go ahead, put in an array of values for the thetas, and pick the one that gives you the maximum shear stress. That's what we're going for. And figure out what that orientation might be. So here we have sigma x equals 50 megapascals, sigma y equals 100 megapascals, and tau xy equals 10 megapascals. So we're going to rotate to get maximum shear stress. And this is just a general description of what we're doing. We got to figure out what this theta s is. Okay? And you can look at the collab there. And when you do that, these are the plots you're going to get. So where do we see the maximum shear stress? What do you all think? Can you see that? Is it too small? What angle would you take a stab at? Where is this thing maxing out? Anyone? Yes, Prisha. I see. Okay, so go ahead. Give me the chop. Yeah. Okay. So like, all right. So like somewhere after 25-ish, right? And somewhere around 125-ish, right? And these are the same, right? Except they're just opposite signs. Okay. And we see that the shear, or the normal stress, okay, at these values is going to be something like this. It's the average. This is very interesting. Okay, so what you're going to find is that the sigma x prime is the average of sigma x plus sigma y, and the sigma y prime is also going to be the average of these two. Okay. So if you go ahead and you do the math, all right, you're going to find that the angle is 34, okay, or so. The tau max is 26.9 megapascals, and then if you go another 90 degrees, you get the minus of that. Okay, so minus 26.9, and in both cases, the sigma is the average. Okay. So those principal stresses, the sigma x prime, sigma y prime, those work out. All right. So let's talk now a little bit about the relationships between theta p and theta s. Okay. So if you look here, and this is just kind of a general thing. What would you say? What is the offset between theta p and theta s? Yeah.
45.
It's 45 degrees. So once you found one, you know that the other one is going to exist 45 degrees off from it, and then you'll get to another of the same if you go 90 degrees. Okay. So this is an interesting property. Okay, so 45 degrees is what separates the maximum in-plane shear stress orientation from the maximum normal stress or the principal stress orientation, right? And vice versa. So a little bit more on in-plane maximum shear stress. Shear without normal stress is possible in a special case of pure shear. Okay, so that's pure shear. This is the structure. This is pure shear on a rod that's being twisted. This is the element under pure shear. You see that? Purposely, there are no, or the sigma x and the sigma y are 0. Okay? So then the orientation of maximum shear may still have normal stresses present. Okay? Yes, that's true. Okay, this is not. Okay, so this case is separate from this case. Okay, just to be clear, or maybe it's not clear. But let me just make that. This is separate. So this is one case. Special case. Okay, and that's what we're describing. That's what we're describing over here. Okay, this is pure shear. And you see this? Then we rotate this 90 or we rotate it 45 degrees. Okay, and we get to what? The normal, the state of principal stress. And what you'll see is that you get a new sigma 1 and sigma 2, and sigma 1 is equal to minus sigma 2. Okay, so I could have, sometimes you'll see when you go from pure shear to the principal state of principal stresses, that you see that they do like one out and one in. In this case, I did them both out, but I just said that they're equal to, they're negative of each other. So this is a separate case. Separate case, because it wouldn't be pure shear. And then this is true for both cases. Uh-oh, and my pen. Come on. Okay. Any questions on this? So this slide is just saying, look, there's a special case of pure shear. It's cool. Be careful. Okay. And then then the last part is just repeating what we already knew, is that the state of principal stress is going to be 45 degrees off of the case for maximum in-plane shear stresses. Okay, and then there will be another question that you get to work on. You know, you don't need me for some of these. You can just go ahead and modify a collab if you like, and you can solve for these problems. All right. Let's talk about a little bit of just a wee bit of calculus that allows us to come up with analytical responses to avoid shooting darts at the board to figure out, okay, where are the peaks? Okay? And if you had to guess, how do you find in calculus, how do you find a local maxima or minima of a function? Yes, Stephen. Yeah, exactly. Take the derivative and you set it equal to 0. All right? So that's all we're going to do. We're going to say, and you're like, why didn't we do this earlier? Well, because we were just trying to illustrate the physical nature of these rotations. And now we're, shortcutting to get answers. But we've already done the physical work. All right, we've exercised our mental physical capabilities. So here's sigma x prime. This is the equation, the generalized transformation equation for x prime. And if we want this to be a maximum, which is what we want for the state of principal stresses, we take the derivative of this expression, okay, with respect to theta, right? Because that's what we're varying. Right? Yes, sigma x and sigma y can vary, but boom, in this case, we've got our sigma x and our sigma y pinned. Those are constants. The same thing with tau xy. The dependent variable or the independent variable, right? The one on which we depend, right? The dependent variable is sigma x prime, of course. So we're varying the theta, and so we're taking the derivative with respect to theta because we're trying to figure out, okay, what's that angle that gets us there? So this term drops away. This coefficient stays, but we have cosine 2 theta becoming minus 2 times that, and we have the sine theta becoming cosine theta, and the 2 from the inside coming out, right? So we've taken the derivative, we're setting it equal to 0, and then what we do, we got to solve for theta, right? So we can write it out like this. We see a sine, we see a cosine, they're on opposite sides. Sine divided by cosine is tangent. All right, so we get now an expression, tangent of 2 theta is equal to this mess. And we can say that now theta is going to be equal to theta P1 or theta P2. So yeah, I mean, this is an equation you can put on your notes. Oh yes, I don't know if I mentioned that, but I think you know it already. You get to bring a second sheet of notes for exam 2. Okay, so you have your first sheet of notes. If you didn't like it, or hopefully you didn't tear it up, or if you haven't picked it up, come. We can pick it up after class, right? So you get your first sheet of notes, and then you get a second sheet of notes. So you could write this on that. This is not an equation though that I go home and dream about. Okay, it's just, and maybe you'll see why. You'll see why once we do some other things later on. This is not how I think about these problems, and not how you'll think about these problems after this exam, or actually maybe even after the next session. Okay, but this equation exists, and we can plug in. Okay, so this is that equation that's going to dictate the angles of rotation, and we can do something kind of fun. Well, I don't know. Again, not something I would do on a weekend, but we'll do it on a weekday. You see that we have this expression tangent of 2 theta, and we can rewrite this expression as tau xy over this quantity like this. What is the definition for tangent, right? Sakatoa, right? Do people still talk about that? Okay, I don't even really remember what that means, but for the longest time I was like, what is this opposite and adjacent stuff when I was a kid? All right, but anyway, we can think of tangent, right, as opposite over adjacent. So what you do is you make a nice little, not unit circle, but you make a nice little nice little triangle. Okay, it's not really that funny. And you have 2 theta here on the inside, okay, for the angle. And then we say, the opposite could be the tau xy, like this. Right, that's that one, opposite. And then the adjacent is just the sigma x minus sigma y all over 2. So that's going to be down here. And then what is this hypotenuse? Well, Pythagorean theorem, right? So it's going to be the square root of these folks. Okay, we're getting there. Yes, you can put one on the other side, but this is the hypotenuse on this side. Okay? So, now, this is maybe not, I was looking at this and I'm like, what did I mean here? This is kind of true, but kind of not true. We're going to look at the original equation, and where we see cosine 2 theta, we're going to use these triangles. Okay, you see that? So what is cosine of 2 theta? P1? Well, it's the adjacent over the hypotenuse. So we can plug that adjacent over hypotenuse right in this whole expression for cosine. And similarly, we can plug in the opposite over hypotenuse over here. Okay? So you didn't have to do like the arctangent, right? You could have, like some people would have been like, oh, I'm going to do arctangent, then I have a 2 theta is equal to arctangent of this thing. You don't have to do that. You could, but you don't have to. You could just use these triangles. All right? Does that make sense? This is not the most important thing in the world, because what is this? This is math. All right? But we're talking about, understanding the orientation and what's happening to the tensor. Okay? And yeah, this reflects that, but this is getting us there. So now we can write out a sigma x prime as this big equation. And people ask, hey, what in the world is blah? What is B? What is L? What is A and H? No, blah is me just not wanting to write this thing again. Okay, that's all blah means. All right. So sigma x prime is equal to this plus this And actually, sigma 1 comma 2 is going to be this plus or minus this. Okay, because there's this one over here that's on this side. Okay. This equation is a good one to write down. Okay, why? Because I'm going to ask you to figure it out, not using this equation, most likely. And then you're going to check your answer on the exam and make sure that what you got is right based on this equation. Okay? Because now going forward, when it says using method of sections, calculate out sigma x prime and tau x prime y prime, you better slice that triangle. Okay? If it says using Moore's circle, which we'll talk about very soon, not today, you better use Moore's circle. But I'm not going to say use the generalized expressions for transformations, okay? Because you ought to be able to do that. Okay, so you can use those generalized expressions to double check what you're doing. Okay. So there will be a question on the exam, or not on the exam, on the homework that has a structure that looks like this. Okay, and you're going to see that there's a state of stress, and so it's going to ask, what is the larger of the two in-plane principal stresses? So how would you do that? You'd go back here and say, what's the larger? Okay, what is the larger? What has to be the larger one? It's going to be this plus this, right? Not this minus that. The minus one is going to be the smaller one. Unless they were both negative. Okay? Then when we say larger, we're usually referring to magnitude. Okay, so then you could be like, which is the has the larger magnitude one? Okay, because they're both negative. But we're not. This one is you've got positive and you got shear stress. I don't think I was. I think I'm just asking what is the larger, and it's going to be positive. Okay, the last frontier. Okay, is calculating in-plane maximum shear stress. And what are we going to do? We're going to do the same exact thing we did, okay? Which is look at the equation for tau x prime y prime, take the derivative of that expression with respect to theta, set it equal to 0, and then figure out what that angle ought to be. And what do you see? We see a sine 2 theta, and we see a cosine 2 theta again. So we get a tangent 2 theta again. And this is that expression. That's the equality. That will tell us where the theta s's are. And if we look at making this interesting triangle, right? If we say this is negative, so that means it's going negative this direction. And this is tau xy, that means it's this direction. And this is the 2 theta in here, okay? Then we can figure out what the hypotenuses are, okay, again. And of course, if we go out of phase, right? We go 180 degrees. Now, see, this is an interesting thing. Remember, we're going theta 90 degrees to get to the other theta s, right? If we have one theta s1, remember we said you go another 90 degrees to get the other theta s2. But we have 2 theta here in our trigonometric equation. So 2 theta is going to correspond to 180 degrees. Yeah, so here's that tau, or that, our tau max, all right? And there's a sigma average, and these are the equations that you have there. Okay? Any questions? So what did we learn today? What if you go home on the weekend, right? Just hypothetically, we are in New Jersey, and a lot of times that happens. It's very nice for you all. That's great. I live here, so I go home. Yes. But what are you going to tell your parents that you learned this week in mechanics and materials, or your loved ones, or your enemies, whatever you have? All right. Someone, or the mirror. You can talk to the mirror. That's fine. All right. What do we learn this week in mechanics and materials? What did we learn on Tuesday? What did we learn today? What are your thoughts? What did the hundreds of dollars that you just spent in these classes, what did you learn? Or why is it useful? Am I allowed to ask that question? No, come on, someone give you an answer. Make me feel a little bit better before we go into the weekend. What is one thing that we learned, in your own words, or mine, what is one thing that we learned this week? Yes, Michael.
Different precedents for calculating shear stress and action angle.
Okay, we learned how to figure out angles. Is that what you said? And yeah. Okay, you're right. And why is that important?
Understanding what the limits
Yeah. Yeah. So we're gonna use these tools when we get to talk about failure criteria. All right. Let's put up the attendance. Give me a second. Give me a second. All right. And I hope you have hold on. Hold on. I'm having troubles here. Oh, that's what, okay.